Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and I haven't been making too many videos lately, but I'm going to resume my daily videos, I think, from this point on, or at least I'll try. And I think one feature I'm going to do on a regular basis now, probably every other day, is a feature on recreational math, kind of fun math problems. And one of those problems is called the Josephus Problem. I don't know how many guys are familiar with this problem. This illustration kind of shows you what's going on here. Um, it's named after, I'll get into the history in a minute, but you're supposed to imagine that there's these prisoners. These guys in the middle of the circle are supposed to be prisoners of war, like Roman prisoners, because Josephus was an ancient Roman Jewish soldier in the first century, and he was, I guess, captured by the Roman authorities. And the problem is that you have these prisoners all in a circle, and they're executed systematically. Every other one in the circle is executed, starting with the first one. So you number all the prisoners from 1 to n, and then you execute every other one, and you keep going like that until there's only one remaining. Pretty morbid problem, but it was an actual. I mean, there's actual historical, records that this problem is a real problem, or at least it was in ancient Rome. So anyway, that's what the problem is. And let me just get into it a little bit more detail. So I think I already kind of said the historical background. It's named after a famous Roman Jew named Flavius Josephus. He was a Jewish historian and a military leader, and he fought. He was, I guess, involved in the first Jewish Roman War. I believe that was the war in which the Romans, invaded the Jewish kingdom at Masada. A pretty horrible thing, and they destroyed the Jewish temple. And, it kind of has personal significance to me since I'm a Jew. But there was a Jewish hero named Flavius Josephus, and I believe he was also a prisoner, but he survived because he was able to compute his Josephus number. He knew how to be positioned in the circle in the right way so that he would survive. Anyway, so the Josephus problem is just the problem I just described. You have n prisoners all arranged in a circle where n is an arbitrary positive integer. The authorities execute every other prisoner, starting with prisoner one, and they keep going until there's only one prisoner left. So the question is, which prisoner remains as a function of n? And if you can calculate that and you can sit in the right position, then you'll survive. I'm not sure if that's what Josephus did, but if he knew how to solve this problem, he would have been able to do that. So, and you can generalize this problem, but it doesn't have to be every other prisoner. It could be every kth prisoner. This is sort of like the that old child's game, eeny, meeny, miny, mo. You go around in a circle and you just kind of count everything that I guess with eeny, meeny, miny, mo, it's every eighth or every 16th or every many things you count each time you do eeny, meeny, miny, mo. But k can be arbitrary. It's the same problem. It just turns out to be much more complicated for general k. So I'm just going to mainly concentrate on the solutions for k equals 2, where you execute every other prisoner. So how do we solve that? Well, the first thing we want to do is we want to look for patterns. I mean, the first thing we do actually is we look for recurrences. This is an example of what's called a recurrence equation. Actually, we're going to end up with two recurrence equations when we solve this problem. So there's really two cases to consider. There's a case where n is even, and then there's a case where n is odd. So let's first consider the case where n is even. In that case, we can write n equals 2m, where m is another arbitrary positive integer. And notice what happens the first time you go around the circle, you're going to execute every even number prisoner, right? So when you're done with that, all you're left with is odd numbered prisoners. And then once you get back, once you've gone all the, once the executioners have gone around the circle once, the problem is really the same problem you started with, because now you have just m prisoners left, where m is half of n, and now all the numbers of the prisoners are all odd, and you can replace k, if k is the kth prisoner, you can replace that with um, 2k plus 1, 2k minus 1, or yeah. I mean, I guess I'm using k to represent two different things here, but k is 2. The first k we started with is 2, so you can forget about that k. But if we're just numbering the prisoners, then the number of the prisoners are now all odd, and we can represent them as 2k minus 1 going around the circle. And so we know that the surviving prisoner is now going to be what would have been the number of the surviving prisoner if there were just m prisoners to start with, and n over 2. Remember, n's even. So another way to say that is that j of 2m, that's j of n, that's the number we're trying to calculate, that's equal to 2 times j of m minus 1. I think you can see that because it's the same problem. We're just replacing the number of each prisoner by twice that number minus 1, and we're replacing n by n. So that's how we arrive at that recurrence. But then we have to do another recurrence when n is odd. And it's the same idea. I mean, it's just a little more complicated in this case. You go fully around this circle, and once you do that, the last prisoner to be executed is number 2m. Now we're letting n equal 2m plus 1. So the 2mth prisoner, or the n minus first prisoner, gets executed. The nth prisoner survives, and then the next one to be executed is the first prisoner, prisoner 1. So now we're left with a circle of prisoners from 3, every odd prisoner starting with prisoner 3 and going up to 2m plus 1, or n if you like. And again, the first prisoner going around this time to be executed will be the second one. So it's the same problem we started with, you just have to renumber things. And when you do that, you find that j of n in this case is j of 2m plus 1, because n is 2m plus 1, and that's equal to 2j of m plus 1. So we get these two recurrence equations from this analysis. We get j of 2m is 2j of m minus 1, and j of 2m plus 1 is 2j of m plus 1. Well, that's pretty nice. And we also have the initial condition j of 1 is 1, because if there was just one prisoner in the circle, he wouldn't be executed. He'd be freed. So this is sufficient to compute j of n for arbitrary n. You just have to keep repeating these, applying these recurrence equations. And you don't even have to do them that many times, because this is sort of binary. Each time you solve these recurrence equations, you're reducing the index by half, roughly. So you have to do about the base 2 logarithm of n times, and then you'll be able to compute j of n. So you can do that. I mean, that's nice. It's not a closed form solution, but you can easily do it on a computer, and you can even do it on pen and paper for small values of n. And when you do that, it's pretty easy to do. You'll find for n up to 16, you get the values in this table. And I think you'll notice a pattern in this table. It's a pretty obvious pattern. First of all, j of n is always odd. It's always the odd number prisoner that survives. I guess that's kind of obvious, because first time around the circle, you're executing all the even number ones, right? So it has to be odd. And not only that, look at what happens here. I mean, for every power of 2, whenever n is a power of 2, like 1, 2, 4, 8, or 16, j of n is always equal to 1. So if the number of prisoners in the circle was a power 2, Josephus would know right away, I want to be the first prisoner, because then I won't be executed. But you'll notice another thing that's going on here. You're counting up by all the odd numbers between each power of 2. So for instance, j of 2 is 1, j of 3 is 3. And then you get to the next power of 2, that's 4. And then you go up by 2 again, 1, 3, 5, 7. And then, from 8 to 15, you're still going up by 2 each time. 1, 3, 5, 7, 9, 11, 13, 15. Finally, 16 is another less power 2, and j of 16 is 1. So I think you can see what's going on here. I mean, we didn't prove this pattern, but we observe it, and then we can conjecture. We can actually write this as a formula. If R and S are arbitrary, um, integers with R I think r can be 0. R is a non-negative integer, but s, yeah, I think they're both non-negative integers, but s has to be less than 2 to the r. If that's the case, then we have j of 2 to the r plus s equals 2s plus 1. That's the formula, which is just another way of saying what I just said, this pattern that we observed. And you can prove this pretty easily. I mean, not really that easily. You can prove it by induction, but I don't want to do that here because it involves two variables. I mean, induction with one variable is bad enough, but you can do this. I mean, you just have to prove that it works for some base values of r and s. Usually you set them equal to 0 or 1. Smallest possible value verified works for those values. And then you show that if it works for an arbitrary, like, so you're probably going to have to fix r here and then let s vary. But then if you assume this formula is true for particular values of r and s, you have to prove that it's true for r and s plus 1, that kind of thing. But then you also have to do induction on it. I just didn't want to do that. But you can do it if you want. Anyway, I think I'll just show a couple examples. So suppose n is 100. Suppose there's 100 prisoners in a circle, and you want to know which position you should be in if you want to survive. Well, you just apply this formula. It's pretty easy. I mean, first thing you do is you look for the largest power of 2 that's less than or equal to n. In that case, that's 64, 2 to the 6th or 64. And then you just take the difference. 100 minus 64 is 36. And you take twice 36 plus 1. And that's the Josephus number. That's the Josephus number. So J of 100 is 2 times 36 plus 1 or 73. So you should sit in position 73 if there's 100 prisoners. What about 1,000 prisoners? I should have written 1,000 here, but for 1,000, the same idea. This time the largest power of 2 less than 1,000 is 512. You subtract 512 from 1,000, you got 488. You multiply that by 2 and add 1, and you get 977. So if there were 1,000 prisoners, you should sit in position 977. Good to know some math. You would have survived in ancient Rome if you were a prisoner of war. So, good thing to know. And, the analysis does get a lot more complicated if k is bigger than 2. You can see how complicated it is here. This is the general recurrence formula for general values of k and n. And you can see it's very ugly. And this is just the recurrence formula. And here I'm writing g of n and k. This isn't exactly the same as j of n and k. It's actually j of n k minus 1 because in computer science people do this all the time. It's much more natural to start counting with 0 than with 1. So if you could number the prisoners from 0 to n minus 1 instead of from 1 to n, the analysis simplifies quite a bit. And that's how we're counting things here with these formulas. So, but you can easily convert that back to the Josephus number when you're done. You just add 1. So, but no, this is just recurrence formulas. I mean, this is nice for a computer though, because like I said, you can compute these. You can solve these recurrences very quickly on a computer. The number of steps you have to do is something like the logarithm of n. So you'll get an answer pretty quickly. But I don't think there's a known closed form expression for general k. That probably is for small values like k equals 3, k equals 4. But anyway, I think you get the idea. So anyway, that completes my video for tonight on the Josephus problem. Thank you for watching. Long live math and long live all of us. It's hopefully we can use math to help us survive, like Josephus did. Anyway, thank you for watching, and I'll see you guys next time.